I'd like to introduce our speaker today. His name is Michal. He's flown all the way from Poland, about a 17-hour trip. So why don't you give a round of applause to Michal?
Does it work? Okay, perfect. Yeah. Hello. Thanks for inviting me to talking today. So my talk is about the security of Fiat-Shamir transformation. So basically, the security of the transformation that allows you to use all these snarks, starks on-chain as non-interactive proof instead of having them like as a communication between prover and verifier. Okay, so before we dive in, let's talk very briefly about zero-knowledge proofs. So in zero-knowledge proofs, we usually have these two parties, prover and verifier. The prover wants to convince the verifier about veracity of some particular statement. Formally, we want to say that particular statement belongs to some predefined language, but we don't need to go into such details now. So prover has like two inputs. One is the statement that it wants to prove, and another is witness. So for example, when you have the statement could be like a circuit C executed on some input A, evaluates to B, and witness could be like all the values from this circuit from very bottom to the top, and right it should end with B. So in zero knowledge proofs, we don't give the verifier the full knowledge of the circuit. We only give the statement of the prover. This also comes from the fact that usually we can write statements in a much shorter way than witnesses. So from zero-knowledge proofs, we require basically three properties. The first one is completeness. So we want to say that if both prover and verifier are honest, then prover will be able to convince the verifier about the veracity of the statement. Another, which I claim is like probably the most important one, is soundness. So here we want to say that if the prover is malicious and the statement is incorrect, then the probability that the verifier will accept such statement is negligible. The different flavor of soundness is knowledge soundness, and this is what we usually use. And this is like a stronger notion of soundness. So here, if verifier accepts the proof, then we know that the prover knows the witness. And finally, we have zero knowledge that we really don't use in blockchain applications, at least for now. So here we say that protocol is zero knowledge if the verifier learns nothing about the witness from this communication with the prover. Okay, so let's talk about how snarks are built. So sorry for this very theoretical slide. There will be few of them here. So starks and snarks start as interactive proof between this prover and verifier. So we design our snarks as protocols where the prover sends some polynomials to some imaginary party called oracles. These polynomials, for example, represent very big computation. So these polynomials are huge. When these polynomials are sent, the verifier also replies with some challenges that also provide some information to the prover how these polynomials should be built. Eventually, the verifier asks this oracle that got all these polynomials to evaluate these polynomials for them. So it picks some evaluation point and gets the evaluations. So finally, the proof is like the set of all these polynomials sent by the prover, along with all challenges that the verifier sent, evaluation point, and evaluation of the polynomials at the evaluation point. So there are a few problems with this approach, namely, like O is like this imaginary party that really doesn't exist in real life, and like since these polynomials represent all this computation, they are huge. So we don't want that. So we need to make like a next step. So for the next step, we use something called polynomial commitments, which basically allow the prover to send like a short digest that represents the polynomial instead the whole polynomial. And importantly, the verifier can also evaluate this polynomial by sending like the evaluation point to the prover, such that this evaluation can be verified. So now we can replace our oracle just by using the polynomial commitments, and that also makes our proof much shorter, right? Because instead of full polynomials, we send these very short digests. So now the communication looks like we have a prover that sends some polynomial commitments, and verifier that replies with these random challenges, eventually replies with some evaluation point, and gets evaluation of the polynomials along with proofs that the evaluations have been computed correctly. So now, like, okay, this is still not great because we have this interaction between the prover and the verifier. So what we do is we introduce a random oracle. So random oracle is like another imaginary entity that is a random function that on input provides some random answer. So now this function is used to compute all the challenges that the verifier would compute itself. So now the nice thing is that the prover doesn't need to talk constantly with the verifier, because it will send something called like partial transcript. So it computes these polynomial commitments, send them to the random oracle, gets a reply, includes the reply in the further computation, computes new polynomial commitments, sends them back to the random oracle, back and forth. Finally, it is able to produce like a single proof for that can be presented to the verifier. And similarly, the verifier itself has access to this random oracle, so can produce the challenges on its own. So now, like the proof is like all these polynomial commitments that the prover sent. They are like included in this proof, along with the challenges from the random oracle, evaluations of the polynomials, and proofs for the evaluation correctness. Yeah, so the problem with random oracle is that, well, it doesn't exist. So what we usually do is like we say, okay, instead of random oracle, let's use hash function. So now the question is like, how secure is such protocol? So now we are going to the core. So the thing with using hash functions and like random oracle as well is that we change a bit the game that we are playing with the prover. So like the verifier now is in a bit different situation than it was before. Why is that? Because when we have like an interaction between the prover and verifier in the interactive proof, and the verifier realizes that that the prover is like incorrect, like tries to claim something wrong, or like some of the answers of the prover don't make sense, then it can always interrupt the communication. So you can think that the communication goes as long as prover makes a mistake, this malicious prover. However, in the case when we have like a Fiat-Shamir transformation, the situation for malicious prover is much better. Because now, the prover, since it computes the challenges that verifier sends on its own, he can predict, by doing computation, he can see whether he can answer these challenges or not. And if he sees like a challenge that he cannot answer, he can just rewind the computation, right? To the very beginning, try to send like different polynomials and can try locally compute a proof that would fit it. So here we have a notion of a lucky set. So basically we can say that some of the challenges that the verifier sends may be particularly good for a malicious prover. So maybe for those who are interested in math, I can add that we usually want to have some polynomials to be equal each other. So I had an example like a few slides back. Let me go here. Here we have this m1x times m2x equals m3x, okay? As I mentioned, like these polynomials are huge, we don't want to send them. On the other hand, we can verify this statement by evaluating the polynomial at random point. Why is that? Because like the probability that this later equation holds when the first line doesn't is like really negligible. And it depends on the degree of the polynomial and the size of the field. Let me get back here, yeah. And here we have also like similar situation, right? If the malicious prover is lucky and it comes to a challenge Z, this evaluation challenge Z, such that, well, even though these polynomials are not equal each other, but they are equal on Z, then yeah, that's a very good situation for the prover. And with non-interactive proofs, the prover can just like try multiple times, right? If we have like an interactive proof, then if I would talk with a verifier that constantly gives me like some bad answers, I would just interrupt connection. Okay. So how to compare the security of interactive and non-interactive proofs? So now we need to say, okay, so our starting point is like saying, what's the probability that an interactive protocol would be broken? And this is, say, some probability alpha, okay? Then we check like the probability that one of the answers from the random oracle, from the hash function, will be from this lucky set where the prover can provide a good proof for a false statement. Finally, we need to include the computational power of the malicious prover, right? Because if the prover is like more powerful, then it can include like much more, they can do like much more trials. Not going into the formulas, but let me only say that the security of the security loss of Fiat-Shamir transformation is roughly like this eta times q. So the probability that the adversary gets a challenge from a lucky set times the power of the adversary. Okay, so how does it affect security? So let's assume that our starting point for the interactive protocol is like 2 to the minus 100, right? So we calculated that an adversary in the interactive protocol who wants to break the protocol has probability 2 to the minus 100 of doing so. And like, what is the realistic queue? It depends on the adversary, right? But if you want to be relatively pessimistic, I would say, okay, let's see like what's the computational power of we have like right now. Like here I looked at Bitcoin network, but it's like it's a bit outdated data. But like you know, like the computational power of world like grows like immensely because of all the of these AI-related things. Also, like Bitcoin at $100,000 as well. So this computational power is like pretty amazing. And the result we have is that we have like roughly like 2 to the 85 hashes per day. That's how much we can compute. What does it mean? It means that the probability that this network breaks the security is no longer like the 2 to the minus 100 is 2 to the minus 15. So if it's like big or small, I would say it's like the probability is relatively big, especially that the compute grows and you don't want to change the parameters of the proof system all the time. Okay, so one thing that is often used in modern snarks are small fields. So in small fields, the challenges from the verifier come from like very small set that also makes the prover much more capable of guessing the challenge or being lucky in having like a good challenge. And there are basically two ways of dealing with this problem. So first of all, what I hope all protocols are doing is that they don't pull the challenges from these small fields, but use some field extensions. But now I would like to talk about parallel repetition, because this is also like technique that works very nicely in interactive proofs, but is totally insecure in terms of non-interactive proofs. So parallel repetition basically says, okay, I as a prover so the prover and verifier run two verification protocols in parallel. So there are like 2 copies of the prover, 2 copies of the verifier. For the prover to accept the proof, both executions need to be correct. Both executions need to be acceptable. And when we have interactive proof systems, that gives us like super nice property, because like the probability here, like denoted by epsilon2, that the verifier breaks both executions is like epsilon squared. So it's like we had like, I don't know, 2 to the minus 32, another 2 to the minus 32, it's 2 to the minus 64. But for Fiat-Shamir transformation, this parallel repetition doesn't work at all. So the thing is that, I don't have time to go into details, unfortunately. So, but I'm very happy to talk about this later. So the main point is that the adversary can partially solve like one transcript and partially solve like another transcript. So the more parallel repetitions we have, then the worse this security loss it becomes. Okay, so and there is more about Fiat-Shamir transformation. So it's easy to implement it incorrectly, so that many attacks shows that. So there's like was a big problem with Plonk because like some teams didn't implement the final final hashing that was discovered by Trail of Bits. And also, it's very important, like when we have like a Fiat-Shamir, not to deviate from protocol description. So like the message I want to say in this talk is that, yeah, we need to use Fiat-Shamir transformation, but we need to be aware that it comes with some security losses, and there is a cost that we need to pay. So we cannot be too aggressive on our security parameters that we pick, and we need to pick them wisely.
Thank you, Michal. Thank you so much. You can never be too careful. You can never be too sure. Everyone, a round of applause for Michal, please. That was a lot, sir. Thank you very much. So we have a couple minutes for questions now. I'm going to point your attention to the screen here, this QR code. So if you have questions for Michal, just scan the QR code. It'll open up the Meerkat app, and you can start plugging your questions in there. The questions will appear on my mobile, and I will probably just read the questions to Michal, if that's okay with you, and he'll feel happy to answer it. Yeah. Oh, I see, okay.
Okay.
Go for it.
So why parallel repetition fails? So the thing is that when we have like multiple copies of the protocol, parallel repetition says that we need to be successful in each of them, right? When we have Fiat-Shamir transformation, and we have these lucky sets. So let me repeat what lucky set is. Like lucky set is like it's a set of challenges such that if the verifier gets a challenge from that particular set, then the verifier is like off the hook. So he can compute the rest of the proof such that it will be accepted by the prover. So the problem with that is that the prover can, in parallel repetition, can like focus on the first transcript, try to get into the lucky set, okay, which it will come with some probability because like as we assume that the fields are small, the space of challenges is small, and then like say save the state, okay. So the prover knows that in the first track it was successful. Then he can focus on other tracks, on other executions, and do the same trick. So like, so the thing is that when the prover is say successful in the first execution, he doesn't need to he doesn't need to care about this execution anymore. He can go to the other, and this when we analyze the probability of the adversary successful, it turns out that the security is like much worse when compared to this epsilon squared. I'm happy to like discuss in more details later. Which concrete properties should a concrete hash function satisfy? So the thing is that as cryptographers define hash function, you know, like we need the collision resistance. This is basically the property. However, we know that there are hash functions that have this property of collision resistance, but are insecure when we try to instantiate like hash function with that. So the thing is that. And there is analysis, but all these hash functions that are insecure for Fiat-Shamir are like some not natural examples. They are not like SHA or Keccak or something. They're like hash functions that were designed to be like insecure for Fiat-Shamir. I don't recall correctly like what's the property of the hash function that it needs to have to be useful for Fiat-Shamir transformation. But if you take any reasonable hash function, it should be good. very challenging selection of small fields, pulling from extensions. Yes. So think like I don't know, Mersenne prime field. It has like roughly like 2 to the 32 elements. So this is like a very small field. So instead of using this as a challenge, you take a challenge being a polynomial of degree 1 over like this, say, f squared, like where the f is the where f is this Mersenne prime, right? So you don't take like a single element, but you take like a pair of elements or triples of elements.
One more question.
Yeah, one more. No, I think I answered all. I probably not. Sorry, maybe there's something like in below, but I don't see it. Sigma protocol. Okay, I will need some time to process it, I think. Coming challenge.
You have maybe a minute.
Okay, so sorry, let me take this offline. Maybe I will be able to quickly answer the quantum security. Like quantum security and Fiat-Shamir transformations are orthogonal problems.